Hello and welcome to Machine Learning First Steps. Today we are going to explain the architecture of a neural network and the basic building blocks which constitute a neural network. So this course is presented to you by Summer. What are we going to do in this tutorial? We're going to understand the basic building blocks of a neural network and how every neuron or building element is connected to the other fundamental elements of a neural network. We're also going to introduce the different activation functions that we can use in a neural network other than the sigmoid function that we've seen before. We're also going to understand the difference between shallow and deep neural network schemes. So let's go. So today I'm going to give a very quick overview on neural networks. So before, we dealt with something called logistic regression, where we had one unit here, and this unit was composed of two parts. One of them was the linear function part, which happened to be a weight W multiplied by the input feature X plus B, and another part which was the sigmoid function. So this was the Z outcome, which was fed later to the sigmoid function to produce something called the activation. So the neural network is pretty similar to that, but the thing is, instead of having just one logistic regression unit, instead we have multiple logistic regression units distributed across layers and maybe several units located within the same layer, as follows. So let's just say that we have some input features. Let's just say we have x1, x2, x3, and x4. So instead of having just one logistic regression in the upcoming layer, one logistic regression unit, we might have multiple logistic regression units. So we might have, for example, 4 logistic regression units, or 5 or 6. It's up to the designer to determine the number of hidden units or number of logistic regression units in each layer. And we don't have to call them logistic regression units anymore. We can call them neurons instead, because in logistic regression, we used to have the sigmoid function as our activation function of choice. But right now, we might have different activation functions that we might use. So instead of just saying logistic regression, we're going to say maybe neurons or hidden units. You can pick one of these terms. So basically what we're going to do here is that each of these inputs will be fed to each of these hidden units. So for example, for this unit here, or this neuron here, we'll have x2, x1, x3, and x4 all fed to that unit. And at the same time, each one is multiplied by the weight. So we've got W11 and W, for example, 12, and W13 and W14. So we have two numbers in our subscript. One of them indicates the number of the neuron to which the arrow is directed, and the second one declares which input feature is being passed to this neuron. So the same goes for the rest of the neurons. So we have another, maybe we can change the color here. So we have these second arrows, these lines. And for the third, we might have something like this. And so on. We'll just keep these three because I have 3 colors here. So we'll just keep these 3. And as a matter of fact, we can have multiple layers. So I can just include another layer of maybe another 3 hidden units. I can change the number of units per layer. So this is a tunable hyperparameter as well. So you can change the number of layers, and you can change the number of units within each hidden layer. So basically, we're going to have the same thing. So the new layer is going to, we can consider the new layer as the input, or we can consider the first hidden layer to be the input feature of the second hidden layer. So in this case, we can do the same thing. We can have that and this. Sorry, I made a mistake here. And this as well. So basically, they are all interconnected together. Sometimes we call that we call these layers fully connected layers, since they happen to be each neuron in one layer is connected to each other neuron in the second layer or in the other layer. And then we have something called the output layer, which I might repeat these layers for, a number of times. It's up to the user to determine what this number of layers would be. And then we have this is called the input layer. All of these layers located between the input and the output layers are called hidden layers. And we have an output layer, and this output layer usually has a predefined size. For example, if you're working on a classification problem as we did before, then this layer would have the same number of would have a number of neurons that is equal to the number of classes that you're going to predict. So basically, if I'm distinguishing between 3 different classes, for example, I will have 3 output units here. Okay. Also, the type of activation function here can be 1 or 2 types, depending on your classification problem. So you either have a sigmoid function because you want to produce outputs that are bounded by 0 and 1, or you might have another type called a softmax layer. And I'm not going to go through the mathematical details of both layers, but let's just say that the softmax layer is another way of representing output probabilities. So they're both used to declare the probabilities of these outputs or of our hypothesis here. But in multi-class classification problems, and also in binary classification problems which use neural networks instead of logistic regression, softmax tends to be more famous. So usually designers use softmax layers for binary and multi-class classification problems when using neural networks, while we use the sigmoid function usually for a logistic regression problem. As for the hidden layers, they can have any number of hidden units, any number of hidden layers, and any type of activation function. There are many types of activation functions other than sigmoid, and we'll discuss that later. So this is basically the representation of a hidden layer, and we get the output hypothesis y cap here. So basically, what happens here is that each of these layers performs the same exact function as a logistic regression unit. So basically, we have the layer here, or we might just have some space here. So basically, our neuron would look like this. So it will be separated into 2 parts. One for the linear function part, which is W transpose multiplied by the input feature X. And this X actually doesn't have to be an X. It doesn't have to be a raw input feature. It might be actually the activation of the layer that precedes this layer. So it might be something like this. And we add the bias, and here we got our activation function. So we can denote this as ak minus 1, like the previous activation. And here we have a different activation function. We can denote this by a instead of the sigmoid function notation, because we might have multiple types of activation functions other than sigmoid. So this is going to be our activation. So basically, this is the output of the neuron, and the neuron might have different inputs as shown here, and the network will basically be composed of many of these units. So what I'm going to talk about next is the type of activation functions that we have and pros and cons of each type. So first of all, as we presented before, we have the sigmoid function, which looks like this, and its mathematical formula is 1 over 1 plus e power negative z, and we have the activation here. So basically, the sigmoid function is very good for demonstrating probabilities, or are very good for any application that requires an output that is basically bounded by 0 and 1. Also, we have another function, which is called the tanh function, which pretty much looks like a shifted sigmoid, so it is kind of shifted downwards, and it assumes the value 0.5 and negative 0.5, and its mathematical formula looks like this. So we got e power z minus e power negative z over e power z minus e power negative z. Yeah, this is basically it. And the tanh function is usually better than the sigmoid function in terms of learning, since it happens to, provide some mapping between positive and negative parts of the curve. So actually, this function could produce negative values, which happens to be sometimes beneficial for the learning process, while the sigmoid here, for example, always outputs a positive number. So this shift might be good for the learning procedure. And usually tanh performs better than sigmoid for the hidden layers, but we actually never use a tanh for the output layer, since the tanh cannot properly um, show the exact probability of the occurrence of an event. So we usually don't use that as the output of a multi-class or a binary class classification problem. And next we have something called the ReLU function, which is one of the newly developed functions. So basically it has a value of 0 here, and then it usually has like this ramp pattern after 0. So actually one might argue that this doesn't quite look like a function which has a continuous derivative, because you can't get the derivative at z is equal to 0. But it's alright, since it is quite hard to obtain a solid value of 0 for an input z here. Programmatically speaking, if you're going to, it's very hard to obtain a solid 0. It's usually something like 0.0001 or negative 0.001, some value pretty close to 0, but never 0. So this is quite rare. And actually, even if it happens, we usually define the derivative at this particular point 0 with some default value. We can pick it to be 0 or 1. It depends on the designer of the API, but it doesn't really matter since it rarely occurs anyway. And the ReLo function happens to be better than both tang and sigmoid for most applications. Since it doesn't quite stabilize, it actually presents a linear behavior, which means the output is not quite bounded for the positive side, which makes it quite good for learning sometimes. So instead of having this stabilization pattern for both sigmoid and tang, we can actually have more potential for learning when it comes to the ReLo function. And of course, the ReLo function cannot be used for an output layer since it doesn't quite represent the probability of the occurrence of an event either. And next we have a function called leaky ReLo, which is, oh, I forgot, actually the mathematical presentation of the ReLo can be written as follows. It's just the maximum value between 0 and z, or z. So if z happens to be positive, naturally we're going to select z as the maximum value, so it's going to be z itself. And if z happens to be below 0, then I'm going to choose 0 naturally. So it is quite, it is a very simple representation compared to sigmoid and tang, but still it has a lot more potential for learning. And we've got a function called the leaky ReLo here. So the leaky ReLo looks like a ReLo function, except that it has a very low slope line, or a very low slope curve here, or curvature, not curvature, I would say, like, instead of having a constant value of 0 for z less than 0, we actually get a linear function that is a function of z, but with a very low slope. So that indicates that this value is going to be very small compared to z because we have a very low slope. And this tends to help with learning, so leaky ReLo is actually sometimes better than ReLo itself because it slightly considers the negative part of the curve, which slightly helps with learning. So the leaky ReLo can have a function or a mathematical representation which looks like this. A is equal to max, some very low slope, let's just say 0.01 for example, z and z. So basically, if z is positive, then z will always be greater than 0.01 multiplied by z. So we're going to pick z for positive values of z. And if z is negative, then 0.01 times negative value is certainly greater than the negative value itself. So we're going to pick 0.01z for negative values. So this is how leaky ReLo works. So usually for most of my applications, ReLo works just fine. And I usually use a sigmoid or softmax units for my output layer. And tang sometimes works better than ReLo and sigmoid in some particular applications. Specifically, biomechanical activity recognition. Tang has proven to be slightly better than sigmoid and ReLo, but for image processing application, ReLo almost always prevails. So it kind of depends on your particular application, and you need to try all of these functions for your application in order to decide which one performs best. So the type of the activation that you're going to select is a hyperparameter that you need to tune as well. Much like your learning rate and number of hidden units per layer and number of layers. So all of these are called hyperparameters that you're gonna need to tune in order to obtain the best possible performance. I'm not going to talk about the process of gradient descent or the mathematical um, basis of gradient descent for neural networks, since we're going to use TensorFlow from now on. So gradient descent just works the same way as before, but now we have like multiple functions stacked on top of one another. So it will work the same way, and we'll use the same chain rule, but we'll use it multiple times in order to get what we want. So instead of just going through that, we'll just use TensorFlow instead. So now we have a new term in machine learning, which is called, it's not actually quite new, but it's been around for like, I don't know, 10 or 15 years, which is deep learning or deep neural networks. So basically we started with something known as logistic regression. We have a point here, we have just a logistic regression unit, and we have inputs going through this logistic regression unit. So this was our first classification example, which happened to be a binary classification problem. So this is a very shallow, this is considered to be a very shallow neural network of only one layer and one hidden unit in that layer. Then we dealt with slightly deeper neural networks, which are still considered to be shallow. Like for example, the network that we've shown before, something like that, for example. So we've got our inputs x1, x2, x3, and we've got like three hidden layers in the first, three hidden units in the first hidden layer, and we actually have one hidden layer, and then one output layer with one output unit. So this is a binary classification problem as well. So basically we have something like this. So this is still a very shallow network. So this is basically what we call a two-layer network. We usually don't include the input layer. We call it layer number 0, which basically means that it doesn't count as an actual layer in our neural network. So basically you start with the first hidden layer. So you basically have one hidden layer and one output layer. So overall we got a two-layer network. Then we might have slightly deeper layers or slightly deeper networks. Then actually, thanks to the huge computational power that our computers possess right now and the evolution of GPUs and maybe also cloud resources, we now have access to much more computational power than we used to have before. This encouraged the evolution, or this helped neural networks evolve into more complex structures. Right now we have like deep neural networks, which I would say that any neural network with more than 4 hidden units, or sorry, 4 hidden layers would count as a deep network. So we would have like our input layer here. So let's just denote that with different color. So let's just have our input layer here. It doesn't matter what the number of input features are. I'm just going to denote this as the input layer, and then we have, like, for example, 5 hidden layers or something like that. And then we have one output layer. So we can call this output, and we are gonna call these hidden layers. So yeah, this is much deeper than our shallow applications. So this is one of maybe the deep network structures that are present right now. One of the earliest deep neural networks. Actually, now we have much deeper neural networks with much deeper structures as well. So this is considered to be like a shallow, deep neural network, but we might have networks that might have like I don't know, 13 layers, maybe 20, 30 layers, maybe 100 layers. Like we might have like very deep neural networks that extract many features. So actually, we might want to understand why deep neural networks work better than shallow neural networks. So let us just display an example here that might help us understand how this works. So if we have, like, for example, audio signals that were recorded and we're asked to determine like which person is this, who is talking basically. So if we have like raw audio signals like that, so they basically don't make any sense. So as a human being, what you do, uh, you're going to extract some features, or you're going to try to extract some features. Like, for example, transform the signal into the frequency domain, maybe, if you happen to be good with signal processing. And you might extract some parameters, like, for example, the frequency. So you might be able to determine whether this is a guy or a girl based on the frequency, because girls tend to have like pitched voices, or maybe their voices are of higher frequencies than most men. Men tend to have like um, lower frequency tones than women. So that might be one feature that you'll be able to extract. And you might to extract more like footprints from this raw data. So what you're trying to do as a human being is you're trying to conduct some sort of analysis on this input and try to extract some features, or try to apply your own activation functions on this raw input in order to get some useful data. So this is basically what a neural network does. But you as a human being, you have knowledge that you've learned. You have learned how to uh, perform frequency domain um, analysis. You know how to write your equations. So you already have that sort of knowledge, which helps you determine your procedure. But neural networks actually are initialized randomly, so they don't have prior knowledge, but they try to learn through the optimization process in order to extract useful features that could actually be able to determine who this person is. So neural networks are trying to develop their own feature extractors. So what happens is, for example, if I get like a deep neural network, let's just say a multi-layer neural network, so I will, for example, feed this input, this chunk, to the first layer. So the first layer may be able to determine, for example, like the peaks of the signal, or the maximum amplitude, something like that. It might be able to determine the initial and final values of the input signal. It might be able to determine other time domain properties of this signal, like, for example, the mean of this signal, and maybe the standard deviation of the signal. So it's trying to learn some like features, or some new features that are different from the raw features that we got before, but at the same time better describe this data, and might actually be like proper footprints. And then these particular inputs will then pass to the next layer. So this next layer might be able to determine more complex features. So maybe this layer is able to, for example, compute the frequency, for example. Or maybe it's able to, I don't know, get other features that might be quite useful in determining who this person actually is. Um, I can't think of um, specific features right now, but it might be able to determine like the pattern of this wave, or might be able to get like the frequency components of this wave and just compare like, for example, just having one frequency feature might have many like multiple, for example, frequency components for this original curve, like many sinusoids, and each one of them having a certain magnitude. Maybe it's able to perform something like Fourier transform, or maybe able to calculate a Fourier series for this input chunk, maybe. And it might be able to determine the magnitude of each sinusoid. And maybe that will constitute like parts of the audio footprint that we're willing to use to determine who this person is. And then it might feed that to the output layer, which eventually decides who this person might be. It might be one of 3 persons, for example, or one of 4 people, who knows. And then what happens here is that each layer computes more complex features than the layer that precedes it. So if this layer, for example, which is the input layer, has the raw features, they basically mean nothing. And then we've got the first layer, which computes like some simple features. And then we might have additional layers which compute more complex features. So as the depth increases, the complexity of the analysis, or the complexity of the functions that the network is trying to learn, increases, which makes it more able to perform more complex classification tasks and include more data. So this is basically the main concept behind deep neural network. And in our next session, we learn how to implement one of these neural networks. It's going to be a shallow neural network, but we're going to use it for a multi-class classification problem in order to show how this actually works. To summarize what we've done so far, we now understand how neural networks work and how to build them. We are now ready to use our software tools to develop a neural network for a multi-class classification problem. And we're going to use TensorFlow for that instead of just implementing the neural network ourselves. So can't wait to see you for our next tutorial.